Hello everybody, this is Aykut Attar from Hacettepe University. So in this lecture, we are going to take a look at the multi-sector version of the Schumpeterian model. So I recommend you to check the part 1 of this model because much of what I'm going to show you today in this lecture depends on what we done with the one-sector model. The reason is simple. Here, yes, there is more than one sector, but all these sectors behave very much like the one sector in the part one. Okay, so this will be a short lecture because again, much of the stuff is already covered in the one sector model. So let me quickly go over the material I have here for you today. Okay, so just to recap, so this is again a Schumpeterian model with creative destruction. The existing monopolies that produce the uh, version of the machines with some productivity level will be replaced by innovators that make up the better versions, higher productivity versions of these machines. So there will be this displacement of earlier monopolists by innovator monopolists in this model. So here what we see the um, final goods sector production function, which is that, and we index intermediate inputs by variable I. So here we just assume that there's this unit interval where these intermediate inputs are located. The production function looks very similar to what we've seen in the product variety model. Here we have output and then labor employed. Then there's this productivity variable here, AIT, and XIT is the number of units of the machine I that is used in production. So once again, we are assuming that the final goods sector firms, there could be many, are perfectly competitive. They're all price takers in all markets. So this is their profit maximizing demand for intermediate input I, right? So this is the inverse demand function that depends, the price they are willing to pay depends positively on productivity and labor. Then, again, we are assuming that each intermediate input is produced by a local monopoly, and there is this one-to-one production technology of the intermediate input. So you take 1 unit of the final good and then produce 1 unit of the intermediate input. Okay, and obviously these monopolies, these local monopolies, know this demand function. All right, this is the inverse demand function. So this is the profit of the monopoly I for period t. So if you solve this, you again get this result, but now conversely to the one sector model, now the optimal level of production of machine I depends on the productivity level associated with that machine. So if you go look at the production function, of course, the productivity is attached to the machine, right? So there's this association between the machine and the productivity level of it. So then the optimal level reflects that result. And if you do the math again, so if you take this and put this back into the profit function here, you end up with optimal profit. Okay, optimal profit again, profit of I in period T depends on productivity level and labor employed. Okay, and there's this fixed parameter here. Now, again, if you are familiar with what happens in the one sector model, this entire setup is same. So there's this success probability. Success probability depends on the normalized research expenditure. So R is the total research expenditure, and AIT star is the targeted productivity at that sector, which is given this way. And remember that innovation takes place at the beginning of period T, right? So you should remember that the solution is just that. And one important result, of course, is symmetry, right? Because every single entrepreneur, because of this normalization assumption, eventually end up with the same level of normalized innovation expenditure. So if you look at the total innovation expenditure, of course, it differs across innovators, but the normalized expenditure is the same, and this is a huge simplification, as you see now. Okay, so if we look at the growth part, we have the symmetry in normalized research expenditure, and that symmetry implies in every sector and at all times, success probability is the same. All right, now in a moment you will understand why this is a critical result. Now, what we define here is average productivity. All right, within this unit interval, there are firms or intermediate inputs whose productivity levels are denoted by AIT, and AT is just the plain average of them. All right. Now, what happens here is that AT will depend on the average productivity of successful and unsuccessful sectors. All right. So why is that important? Well, we know from the one sector models that growth was stochastic there, right? So in one period, let's say in period T, either there is innovation or not. For this reason, growth was fluctuating between 0 and gamma minus 1, right? Gamma minus 1 is basically the step size minus 1. So that's the growth rate if innovation is successful, right? Now, in reality, we do not observe that. Of course, in reality, we have more than one sector and we have more than one firm within each sector that innovate or not, right? So what happens in the multi-sector model is exactly this. Okay, so there will be some sectors that will be successful in innovation, all right? So when they get successful, of course, their productivity will increase from AIT minus 1 to AIT star. And there are unsuccessful sectors, so their productivity remain at AIT minus 1. Okay, so what we have here is that this average depends on the average productivity in the successful sectors and average productivity in the unsuccessful sectors. And here is the catch. So since this is same for all innovators, since this is same for all sectors, the law of large numbers apply here. So this is like since we have more than one sector in the economy, some of them will be successful and some of them will be unsuccessful. And those fraction of successful sectors and fraction of unsuccessful sectors will depend on this ex ante probability. All right. So this is known as the law of large numbers. More specifically, it is the Borel's version of the law of large numbers. And law of large numbers allows us to write this equation. All right. And we have A1t here, which is equal to gamma AT minus 1, and A2t here, which is equal to AT minus 1, because that average does not change. All right. Unsuccessful sectors are here. So then this is the weighted average of successful versus unsuccessful sectors. So there is, of course, some, so we can actually write, going from these two equations to this equation a bit more with some detail. So if you look at my 2019 paper on Turkish economy, I'm actually doing that in some part of the paper. Just let me know if you don't have the access to it, so I can send the paper to you. And this is true for everyone, not just for my students. So if they let me know that they want to see the paper, I can send it. But what happens at the end is that, thanks to the law of large numbers, which requires this result that we obtain in the optimization problem of the innovators, we end up with non-stochastic growth, right? Because now growth is not fluctuating. At each t, we see productivity increase because we know that since this is positive, since mu is strictly positive, we always see some success in the economy, and that success eventually translates into productivity growth. All right. So because these sectors with some positive probability, this is the again this is both the ex ante probability of being successful at innovation in each sector, and also the ex post fraction of successful sectors. Okay, so thanks to this result, we observe growth in each and every episode, and since mu is constant and gamma is also constant, the step size, the growth rate of productivity is constant in this economy. All right, so that's basically it. Again, just to recap, so we extend the production function of the one sector model with the multi-sector version. So we have more than one intermediate input located within this unit interval. The rest is the same until we try to write what happens to average productivity, right? And then we understand that thanks to the law of large numbers, this average productivity could be written simply in this way. So the average productivity growth in the economy will be just equal to mu times gamma minus 1. And of course, mu is just coming from this. So mu is positively depending on L as well. So we're going to cover that scale effect issue in later lectures. And there's one more remark I want to share with you. So in this model, we have the unit interval, right? But we can add to this model the product innovation aspect by making the number of intermediate inputs an endogenous variable. So a simple version of it is shared in the textbook, I think in the same chapter, chapter 4. Aghion and Howitt introduce MT here instead of just 1. There's this unit intervals 0 through MT, and MT becomes an endogenous variable, endogenous stock variable of the model, and it depends on entrepreneurship and the firm exit rate, because some people serendipitously invent new intermediate inputs, so they become the monopolist of these inputs, and then also some of these intermediate inputs are dropped from the production process. Okay, so I want you to check that very simple extension to this model, because it will be also related with this scale effects discussion. All right, so that model will be more like a second generation Schumpeterian model that we covered in later lectures. Okay, I think that's all for today's lectures. Again, if you get confused about the law of large numbers, just let me know and I can send you my 2019 paper on Turkish economy so you can understand the transition from these two equations to that equation better. And that's all. Thanks for watching.